Hello and welcome to the Things Summer Academy. I am JP Meyers and I'll be presenting the LoRa range testing workshop. Shortly after the Things network started, I had my first gateway set up and some devices sent messages through it. But I wanted to know how well this new technology actually works. So I started measuring the distance I get with different gateway configurations and different devices and antennas. Because other users of the network also wanted to do the same, I shared my tools with them. This became what is today known as Dtmapp. In a previous workshop, you have built the LoRa gateway. Today we will use the Arduino you have programmed to test how well the gateway works and how far a LoRa signal can travel. But first, let's recap on the theory of how radio waves propagate. For now, just listen and take notes. We will get to using the Arduino and gateway in the next section. We are going to simplify a lot of the theory to only the key things that influence range. If you are interested in more, there are YouTube videos available by Thomas Telkamp and Andreas Spies that explains more of the details. I'll provide links at the end. Radio waves travel in a straight line. In this case, we have uplinks from the user to the tower and downlinks from the tower to the user. Radio waves can be blocked. They also become weaker as they travel through different objects. The amount at which the waves are attenuated depends on the material they are passing through and how dense this material is. A tree is less dense than a concrete wall, so a concrete wall will weaken the signal more than a tree. Radio waves can be reflected. Reflections can be good, as it may allow you to communicate around corners. Reflections can, however, also be bad, as a reflected wave is out of phase with the original wave, and can therefore cancel the original signal out. This is also known as destructive interference. For more about this, it's good to read up on the Fresnel zone. Radio waves can be bent, scattered or refracted. This may allow you to communicate across a rocky mountain. Radio waves become weaker as they travel. We call this free space loss. This is mostly caused by the energy spreading out spherically from the origin. Again, it's important to know that radio waves can be blocked, also by the curvature of the Earth. This becomes apparent if you want to communicate at a long range. One important concept when it comes to radio communication is noise, or more specifically, the noise floor. But what is noise floor? It is the hiss or hum that is always present on the radio band. Let's get an FM radio and hear what happens if we tune it away from a radio station. What did we hear? Noise? Yes, this is the noise floor. But where does this noise come from? All matter is built up of atoms, and these atoms have vibrating electrons around them. Moving electrons causes an electric and magnetic field. The warmer the matter, the faster these electrons vibrate, and the stronger these fields will be. Noise also comes from above, from the stars. That's called cosmic background radiation. And all electric appliances have electrons flowing through them, which again causes noise. The combination of all these noise sources causes the ever-present noise floor in the radio spectrum. If we look at the radio signal on a spectrum analyzer, we will see the strength of the signal as a spike in the middle and the noise floor on both sides of it. The signal strength is the height of the peak. The RSSI value is an estimate for this strength. The noise floor is the horizontal zigzag line at the bottom, and the difference between these two is called the signal to noise ratio. For communication to be successful, the receiver needs to be able to hear and understand the transmitter. Imagine you and a friend talking to each other at a music concert. There is a lot of loud music, which is background noise for your conversation. It's quite difficult to hear each other, and normally one will start to shout at each other. It's the same with radio. The signal needs to be strong enough to be heard above the noise. A gateway in a noisy environment cannot hear end devices. LoRa is, however, special, because it can be heard and understood even if the noise is louder, but only if the noise isn't too much stronger than the signal. LoRa signal strength is indicated by the parameter Rssi, or Received Signal Strength Indication. Rssi is measured in decibel milliwatt, or dBm. Rssi is normally a negative number, with a less negative value being better. The minimum Rssi that we would see for a standard LoRa signal is about minus 120 dBm. The maximum depends on how close you are to the gateway, but a signal of about minus 80 dBm is very strong. Anything stronger than this may damage your gateway. At 868 MHz for a 125 kHz wide LoRa channel, the theoretical noise floor is about minus 120 dBm. That's why we will almost never see an Rssi value lower than this. Signal to noise ratio is the second parameter we have to see the quality of a LoRa signal. It is measured in decibels. A positive signal to noise ratio is good, while a negative signal to noise ratio is bad. A normal range for SNR is between 10 dB and minus 10 dB. The Rssi value of a signal will go down when the distance between the end device and the gateway increases. Any obstacles between these two will attenuate the signal and also cause the Rssi to decrease. In both these cases, the noise floor remains the same, which means a decrease in the Rssi will also cause a decrease in the SNR. SNR will also decrease in a noisy environment. If the Rssi remains the same, but the noise floor increases, the SNR will need to decrease. If the signal strength drops below the noise floor, or if the noise floor increases above the signal's strength, we will see that the SNR becomes negative. In this scenario, the Rssi will indicate the noise floor's level and not the signal's strength. To get an indication of the signal strength, we can subtract the SNR from the Rssi. By looking at only the Rssi and the SNR, we can identify a couple of different scenarios. A device close to a gateway will have a high Rssi and a high SNR. A device far away from a gateway will have a low Rssi and an average SNR. A device very far away from the gateway will have a low Rssi and a low SNR. A gateway in a noisy environment will have a high Rssi but a low SNR. Using LoRa, there are a couple of transmission parameters one can change to improve the performance of the radio link. One of the most common ones, which is also used by the adaptive data rate system, is the spreading factor. But what is the effect of spreading factor on Rssi and SNR? A higher spreading factor spreads data out over a longer time period. This means more energy is used per bit of data. If we look at the spectrum analyzer while we increase the spreading factor, we will see no effect on the Rssi. The noise floor is also not affected, so the SNR will also remain the same. But if both the Rssi and the SNR remains the same, why does a higher spreading factor gives longer range? Well, it's because there is more energy per bit. On the receiver side, we listen for longer, gather more energy, and can make a better guess what is said because we have more energy to decide. Mathematically, what we do is an integration, so we sum the energy, and in the process, the noise will cancel out. We can compare this again to two people speaking at a music concert. They end up shouting one word at a time, very slowly. If you are learning a new language, it is also common to ask people to speak slowly so that you can understand. At a higher spreading factor, the signal is receivable in a more noisy environment. What we will therefore see is more signals are received at more negative signal-to-noise ratios. Semtech published this table that indicates the minimum signal-to-noise ratio value that is receivable per spreading factor. The higher the spreading factor, the more negative signal-to-noise ratio is acceptable. Let's have a look at what makes a good and a bad gateway. If a gateway is installed outdoors, there are less obstructions to block the signals. But even outdoors, one needs to install it in a location with a clear line of sight to the area where your devices are installed. Try and install it above the trees and roofs in the immediate vicinity. Some areas are noisy and will deafen the gateway. There's very little we can do about this. Using a good antenna at the correct frequency for LoRa is very important. Height above ground is a double-edged sword. The higher you install your gateway, the more areas it will be able to see without any obstructions. But the higher you go, the more noise is received. Now let's have a look at what affects the performance of an end device. The location where it is installed is very important. Ideally, you want the device to have a clear line of sight path to the gateway. A device on the roof or outside of a building will work better than a device inside the building. A device underground or on the floor will likely perform very poorly. An antenna on the outside of the enclosure of a device will perform better than an antenna inside the enclosure. The orientation of the antenna also has an effect. Ideally, we want both the antenna at the gateway and the antenna on the end device to be vertical. But in practice this is quite difficult, as one can't always choose where and how the device is installed. Choosing a good antenna at the correct frequency for LoRa is very important. Do not use GSM, 3G or similar wideband antennas. Choose an antenna that is specifically designed for 868 MHz if you are in Europe, or the frequency used in your area. An important thing to be aware of is that not all glass is transparent to radio signals. Some glass contains metal or has a metal coating. This metal layer will block radio signals. When installing a sensor in a car, plan to get the signal out of the front window, as these are normally designed to allow radio signals through, while the other windows in the vehicle will block it. This was a quick recap of the most important things to know to test the range of LoRa. If you are interested in more details, have a look at these two videos by Thomas Dalkamp and Andreas Spies. In the next section, we will have a look at the metadata of your Arduino on the Things stack console. In this section, we will use the Arduino Maker WAN 1300 to do a simple LoRa range test. You can however use any other end device as long as it sends uplink messages periodically. To follow along, you need the Arduino IDE installed along with the Arduino SAMD board definitions and the Maker WAN library. If you followed the LoRaWAN devices workshop this morning, you should already have these installed and have your Arduino delivering messages to the T10 console. We will do a quick recap. When you take the Arduino out of its box the first time and power it up, you will see the orange LED flashing, like you can see in the video down below. To get the Arduino talking to the Things network, we can follow the guide from the Arduino website, this one, how to connect Maker WAN 1300 and Maker WAN 1310 to the Things network. I'm going to do a quick demo of how I do these steps. So open the Arduino IDE, and I already have the libraries and the board definitions installed, which means under examples I will see the Maker WAN library and I choose first configuration. I verify this, and before I upload it I open the serial monitor and now I say upload. Okay, done uploading, and it starts with a welcome message. And now what we need to do is we need to use this EUI to register this device on the Things network. So I copy that and I open the console. I already created an application for my devices, and in this application I say add in device. The brand is Arduino. The model is the Maker One 1310 or 1300. The region I use is Europe. The frequency plan I use is the recommended one. The app EUI we don't have, so we choose this option for with zeros. The device EUI is the thing that I just copied from the serial monitor, so I paste this in here. And the app key I generate. Now the next step is to click on register in device. In my case I already registered this device, so I'm not going to click there, but it will look the same as what we have here. So to complete the steps of the first configuration, we need to say 1 year because we're using OTAA. Then it asks us for the app EUI. App EUI is this value we copy here, and we paste it in there. And the app key is this one. I copy it here. And now because I know what's happening next, I'm going to go to live data in the meantime and clear here. And the value I paste it in there. And now we wait. And now the device is join a request. And we're just waiting for the first message. Message sent correctly. Now it should appear there. There we go. So this is the first message sent by our Arduino. We've got firstly the parsed payload, the JSON object. Our parser wasn't able to get the LED state out of it, so that's why it's null. Then we have the binary payload in hex here, followed by the port we used, which is 3. Then the data rate, so it used spreading factor 12, bandwidth 125 kilohertz, followed by the interesting part, which is the signal to noise ratio and the RSSI. So we've got an RSSI here of -89. That's quite good. And we've got a signal to noise ratio of 9.5, which is very, very good. Remember we said we expect a signal to noise ratio of between -10 and 10, and we expect an RSSI value of between -120 and -80. So these are both on the upper edge of the ranges we expect. If we click on this, we get to see more metadata here on the side. The interesting part is the Rx metadata. The Rx metadata is an array containing all the gateways that received our message. So in my case, I've got 1, 2, 3 gateways that received my uplink message. The first gateway received it at an RSSI of -89. That's the same values we see here. So the values we see here in the smaller form is only the first gateway's values. The second gateway received me at a slightly higher RSSI value and also a signal to noise ratio of quite high, a 9. The third gateway, however, we see an RSSI of -121, which is the lower limit that we would see, and a signal to noise ratio that is negative. And in this case, it's quite negative. So this gateway, the last one, barely received us. And these two top gateways that received us were very well. So I've got 2 very good gateways here and a gateway that's not good, performing well. So this gateway, because both are negative, I assume this gateway is very far away. Just judging the signal from a single message is actually not good enough. So the next thing that I'm going to do is I'm going to change the Arduino code to keep on sending messages so that we have more messages to look at and to judge the signal from. So let me open the Arduino environment again. The sketch I'm starting with is the example to LoRa send and receive. So open this one up. By default, this sketch only sends messages when you press a button on your keyboard. So I'm going to change this. I already changed this, and you can copy the code from GitHub. If you go to this URL, I will provide a QR code for you to easily find this. So I copy all this code, which is just a modified version of the LoRa send receive. I copy this and I replace the entire code for the LoRa send receive here. So this code, if you look carefully here in the loop, it sends a message, begin packet, end packet. it delays 10 seconds and then it tries to send again forever and ever. So every 10 seconds we should see a message coming in on the Things Network console. Second thing to do is we need to paste in our keys here again. So I go back to the console. I copy my app EUI, paste in my app EUI, copy my app key, paste in my app key. I say verify, and I say upload. And while that's uploading, I'm going to go to the live data here, and I'll just clear what we've seen here. And if all went well with the upload, we should see a join, yes. And then any second now, we should see an uplink message as well. Yes, there we go. And then 10 seconds later, we should see another one. 4, 3, 2, 1. Yes, there we go. So every 10 seconds, we should see an uplink message coming in here as well. If we go back to Arduino quickly and look at the serial monitor, what we see here is TX result equals 0 every 10 seconds. Sometimes the duty cycle limitations of the LoRa band doesn't allow us to send every 10 seconds, and then you will see different TX result here. But every 10 seconds with an empty frame or empty packet like we send here should work most of the time. So now what we can do is on the console we have multiple messages, and we can keep an eye on the RSSI values here. So of course the order of the gateways we're not sure about, so we need to, in the case of multiple gateways like me, I need to open this again. And actually this is interesting, I only see 2 gateways here. 1 gateway, 2 gateways. The third gateway doesn't receive me this time. But we can easily now see the signal to noise ratio jumps around a bit. The RSSI value jumps around a bit. And now I have to confess something. I didn't plug in the antenna for my Arduino. This was on purpose, and I do not recommend you to do this. You should always have an antenna plugged into your Arduino because you can damage the hardware. So let me quickly plug in the antenna. Carefully. There we go. So it's the normal Arduino antenna I have here, this one. I'm just going to put it down there next to it on the empty cardboard box Arduino came in. And now let's wait another 10 seconds and see what happens. There we go, TX result equals 0. And it was received. Yes, that's a big difference. So we jumped from an RSSI of -85 to an RSSI of -30. This is way too high. The poor gateway right next to me is being shouted at. And in this case, we might damage the gateway. But in this case, for my example here, this is very clear that plugging in an antenna is much better than not having an antenna plugged in. Another interesting thing to look at here is the number of gateways that received us. So we again back at 3 gateways, 1, 2, 3 gateways, and the gateway was that barely received us the previous time. That was at -121 the previous time. Now is receiving us at a very strong signal of -69. This specific gateway is actually on my roof, so we've got metal roof tiles between the device and the gateway. And without an antenna, the signal doesn't want to travel through those metal roof tiles. But with the antenna plugged in, we actually get the signal through, and it's going through quite well. I'm now going to unplug the Arduino from the computer. So the serial monitor will disconnect. I can close that now. I'm going to clear the log file here. And I have a USB power bank. I'm trying to show it to you here in this little video, with a short USB cable on it, and I'm going to use this to power my Arduino. The reason I'm doing this is so that I can walk around with the Arduino. It's powered up again, and if all is well, yes, we see the join accept, and in a few seconds we should see our first uplink message. Yes, there we go. Signal to noise ratio 8.5, RSI -39, that's very high. So now with the Arduino being mobile, we can go and walk around and do a proper test. I have the console open on my mobile phone now, looking at the live data for the specific Arduino I'm using to do the test. You can see here, if you scroll sideways, you've got the signal to noise ratio and RSSI values here. It's not the best user interface for mobile, but at least we can see the SNR and RSSI while we walk around doing testing. Because Arduino is plugged into a USB power bank and my phone is running off of battery, I can take these two devices in my hands and walk around the block, and maybe walk as far as I can until I stop seeing messages arriving here. As I walk away, I should see the RSSI drop and the signal to noise ratio as well. And as I walk back, the RSSI should increase again and the signal to noise ratio should increase as well. So it's a usable solution to do LoRa range testing, but it's not ideal. In the next section, we will do a demo of the Dtmapp Android app that will help you make this much easier. In the previous section, we looked at the metadata on the ThingStack console. Specifically, the RSSI and SNR values gave us a good idea of how well our device is heard by the gateway. Looking at the metadata on the console is tricky, especially when you are walking around doing range testing. To make it easier, there is the Dtmapp mobile phone app. Currently, only the Android app supports the ThingStack version 3. The iOS app currently only has support for version 2. We will therefore do this demo using the Android app. On your smartphone, open the Play Store and search for Dtmapp. You should find an app called Dtmapp Phone Surveyor. This is the one. Click to install it. After it's installed, click Open. You should see a map with 3 tabs at the bottom. The first thing to do is to link our testing device to the app. To do this, we go to Settings, and then we click on the Link a New Device button. The app supports 3 different network servers. We are using the ThingStack version 3. To link a device, we need 4 pieces of information. This info is available on the console. We send the Mapper app to the background and open our browser. In the browser, we go to the console for our region. Log into the console if it is required. We click on Go to Applications, and then we choose the application that contains the device we are testing with. On the top left, we click the 3 dots to open the sidebar. Then we choose the integrations and then click on MQTT. Under connection credentials, copy the first field, the public address. Go back to the Dtmapp app and paste this value under the public address. Go back to the console and copy the username. Paste this into the Dtmapp app. For the password, we generate a new API key and copy it. And we paste this into the app. The last thing to configure is the in-device ID for the device we are testing with. We go back to the console and choose End Devices. We click on our end device and copy the end device ID. We paste this into the app. Now we click on Link Device. Under Link Device on the Settings tab, we will see the information we just entered. An MQTT topic was automatically built up for our testing device. Let's go back to the Map tab. At the bottom, we see the message GPS stopped and MQTT disconnected. Let's click on the blue play button to start our range testing experiment. The app asks for location permission. This is required because we use the phone's GPS to determine where our device sent the message and allow us to indicate the signal on the map. The app also asks us if the app may run in the background while the screen is off. This requires us to disable battery optimization for this specific app. Let's try starting the range testing experiment again. At the bottom of the screen, we will now see MQTT connected and hopefully GPS location valid. If your GPS location is not valid, try going outside where you have a clear view of the sky. The app is now in recording mode. Every time your device sends out a message, the app will receive it via MQTT from the things stack. Because we assume you have both your end device and your phone in your hands, we can use the phone's location to geotag the messages. On the map, we can then draw a marker for every message and color them according to the signal strength. A warm color like red is a strong signal. A cold color like blue is a weak signal. This will create the heat map of our coverage. Because the metadata contains all the gateways that received our end device, and sometimes the location for these gateways, we can draw markers for these gateways and lines for the path that the radio signal followed. Let's power up our end device and see what happens. We can see markers on the map, which means everything is working correctly. To stop the range testing experiment, click on the pause button at the bottom left. If you want to clear the data from the map, you can force close the app. Let's go for a walk around the block and see the coverage for our gateway. Sometimes one wants to map coverage over a longer time, or you do not want to keep your phone awake while mapping. And in some situations there isn't an internet connection available for your phone and the app to use. Therefore, the most common way of mapping a gateway's coverage is by using a GPS tracker. A tracker has a GPS receiver on board. It can therefore determine its location by itself. The tracker then sends this location in the payload of the LoRa message. On the things stack console, one can send these coordinates along with the metadata of the message directly to Dtmapp. Let's hook up a GPS shield to our Arduino. One would normally use the Arduino Maker GPS shield, but I do not have one of these. I'm using an old SparkFun GPS logger shield that is meant for the Arduino Uno. These two shields should work the same. Only the electrical connection will look less tidy with mine. Gonzalo Casas has made an example GPS tracker sketch for the Arduino Maker WAN. Go to his GitHub and download a zip. Extract it, then open the Maker WAN 03 GPS tracker example. Also have a read through the README which explains the electrical connections which are necessary between the GPS shield and the Arduino. Again, copy your keys from the console and paste them into the Arduino secrets.h file. Now I'm putting the box with the Arduino GPS shield and USB power bank outside so that the GPS can obtain a GPS fix. Let's look at the console to see if we are receiving messages. The payload is showing some hex values which we still need to convert to coordinates. Let's add a payload decoder. Gonzalo provides the appropriate one in the README. Copy it and click Save. Back on the Live Data tab, we will start seeing the decoded payload, which includes altitude, h-stop, latitude and longitude. To send this data to Dtmapp, we need to add a webhook. In the left-hand menu, go to Integrations, Webhooks, and then choose Add Webhook at the top right. From the list of templates, choose Dtmapp. In the webhook ID field, type any name for this webhook, something like My Dtmapp webhook. A valid email address is required to identify who is providing this coverage data. If you are not sure your firmware is working correctly, or if you are mapping coverage from an unrealistic location like a weather balloon, provide an experiment name. Otherwise, leave the experiment empty. Click Create Dtmapp webhook. The steps we followed here can be used for any GPS tracker device. As long as the device is providing a latitude and longitude in its decoded payload, Dtmapper can make use of this data. Everything is now in place for you to go on a range testing drive. Have another walk around the block. When you come back, we will analyze the data we have gathered using the Dtmapper website. In this section, we will analyze the data from your range testing experiment. As an example, I will look at the data from the test I did using the Android app. On your computer in a web browser, go to dtmapper.org. This webpage shows the coverage for the Things Network Community Edition. You can use this website to determine where there is coverage and therefore where you can install your sensors. The map you see is built up with crowdsourced data contributed by people like yourself. Anyone can do range tests and provide data to improve these maps. To see our gateway or our end devices data, we go to Advanced Maps at the top. To see our devices data, we need to enter the device ID here and then choose a time range. Choose the day that you went to walk around the block, then click View Map. We can also filter by gateway ID by entering the gateway ID here and again choosing the time range. Here is the result from my walk around the block. We can see red dots and lines going to the north. This means the signal is good. To the east and southeast, the colors become more yellow and green, so slightly weaker signals. In this direction, there are more buildings in the way. To the northwest and southwest, we have green dots and lines. This is the weakest signal during the test, at a maximum distance of about 230 meters. This is in fact the indoor gateway, and we do not expect a range more than 100 meters. Fortunately, I have another gateway on my roof. This gateway received me all around the block, and the colors are quite warm all the way. We can therefore clearly see the difference the installation location makes on the performance of the gateway. If we zoom out a bit and look at more data for this outdoor gateway, it really looks like a good gateway. But let's compare it to another outdoor gateway just outside our city. These two gateways can both reach very far, but the second one has more far links with warmer colors. We can immediately see the second one performs better. But why would this be? It's because the noise in the city deafens the gateway on my roof. The gateway just outside of the city has less noise and the range is therefore better. Let's also compare my device with two other devices. This is the result I got with the first testing device, and this is the result I got with the second testing device. This device performs really poorly. It was only receivable by one gateway and at the maximum distance of 160 meters. The colors are also mostly cooler colors. My third testing device performs slightly better. The colors are slightly warmer, and the maximum distance I got here was 260 meters. It was also received by a second gateway at more than 4 kilometers away. Why do these devices perform so differently? The second one has an internal antenna that is not specifically meant for 868 MHz. The third one also has an internal antenna, but it's a good 868 MHz antenna. The first one that performs the best has an external antenna, just like the antenna on your Arduino. Now that we are at the end of this workshop on LoRaWAN range testing, let's summarize what we have learned. Radio waves travel in a straight line, but there are many factors that block or weaken them. Gateway performance mostly depends on where they are installed. Device performance also mostly depends on where they are installed. RSSI and SNR indicate if our device and gateway are performing well or not. We can verify our coverage by doing a range test. The metadata from this test will tell us if the signal is good or not. We can use the Dtmapper app to help us, or we can use a GPS tracker for this. Some gateways work well, others don't. This is mostly due to their installation location and the amount of noise the gateways hear. Some devices work well, others don't. This is mostly affected by installation location and the antenna. RSSI and SNR values are our friends. Your assignment for this workshop is to do a LoRa range test using your gateway and your Arduino. Power the Arduino with a USB power bank or with a laptop. Go for a walk with your laptop or smartphone and keep an eye on the RSSI and SNR values reported on the console. If you have an Android smartphone, you can use the Dtmapp app to help you. If you have an Arduino GPS shield, you can use this to build a GPS tracker. With a GPS tracker, you can drive around in a car and analyze the signal afterwards on the Dtmapp website. I will be available in the chat in case you have any questions. Thanks for your time. I hope you learned something new today. Until next time, goodbye.